So in the afternoon session, we have four more invited talks, and we have another poster presentation. So we are already behind schedule, so let's start. First, we have Sergey Levine here. Uh, so Sergey is, do I even need to introduce him? Sergey is an associate professor at the Department of Electrical and Computer Science at UC Berkeley. His work focuses on machine learning for decision making and has worked in like lots of different areas in decision making and control. So I'll hand it over to him. He'll be talking about general purpose self-supervised RL.
All right, can I share my screen?
Yes.
There we go. Okay. All right, can folks see the screen?
Not yet. Just give us a second. No, don't share. Just maximize on there. Okay, I think we are ready.
Great, thank you. And thank you for the introduction. Apologies, I couldn't be there in person. I will actually be coming to Amherst tomorrow, but due to some last minute travel issues, I couldn't make it today. I'm going to talk about general purpose self-supervised reinforcement learning. So this workshop is ongoing beyond rewards, and I'll talk about how we can go beyond rewards. But before I do that, I want to discuss a little bit of perspective about large-scale machine learning problems. So these days, I think large-scale machine learning really is on everybody's mind. Deep learning at some very basic level is about taking really big models. These days, these would be giant transformer models, putting them on tons and tons of GPUs or TPUs or something like that, spending lots of money on lots and lots of compute, and doing all of that with really big data sets. And across a range of domains, from computer vision to NLP, these seem to be the ingredients that really make things work. And the data sets are really the essential component of this. Traditionally, in kind of the pre-self-supervised learning era, these data sets were labeled manually by hand. But these days, of course, the alternative that folks use in everything from large language models to self-supervised computer vision systems is to use relatively smaller labeled data sets for fine-tuning that basically represent their task, and very large data sets that are scraped from all over the web that are very heterogeneous, that represent a lot of different stuff in them, aren't necessarily very, very carefully curated and certainly not labeled, but really emphasize scale. These are these kind of, that I might pejoratively call them garbage data sets, not in the sense that they're just really bad, but in the sense that they are not really filtered. They're not curated for the task. And that's a really powerful recipe because the capabilities of these models are determined by the size of the data set. So if you want the biggest data set, you're just going to scrape everything that you have available to you. And self-supervised learning methods like next token prediction, contrastive learning, all that stuff, they're really, what they excel at is distilling these garbage data sets into really good pre-training. But it's very reasonable for us to then ask the question, well, a lot of the knowledge in these models stems from that pre-training process. Where does that knowledge come from? Where does the knowledge come from for diffusion models, for language models, chatbots, etc.? If it's basically classical unsupervised learning, it's modeling the distribution of the data. And the data is all this stuff that we scrape from the web. So it's kind of like a really scaled up version of what we learn in like statistics class when we learn about fitting densities, except now in like very high dimensions and with extremely large data sets. So this is a purely data-driven process. It's nice, it's mathematically principled, but ultimately it's just learning about what from whoever collected the data. And if this is data scraped from all over the web, it's basically learning from like random people that put photographs on the web and random things that people typed on keyboards. So it's not actually like a very intentional distribution that necessarily reflects any task we particularly want to solve. And that's kind of an issue because this is in some ways antithetical to this principle that we want to squeeze whatever knowledge we can get out of uncurated garbage data. Like it turns out that the distribution of the data actually really matters. So there's this tension that we have to resolve. And current self-supervised learning methods, in my opinion, don't actually resolve this tension very well. And maybe that's why we get into all sorts of trouble with things like prompt engineering, where taking these self-supervised models, like language models that are doing next token prediction, and then coercing them to solve a particular task requires a lot of very ad hoc effort. And perhaps that's because the pre-training process is not actually as resilient to having just garbage data as we might like. Okay, this is all a little bit philosophical, so let me get even more philosophical before we actually drill down into the specific methods. So stepping back a bit, if we want to start thinking about a way to do this better, we can ask a very basic question. If we want a better way to do self-supervised learning, well, better for what? Like, why do we need machine learning? And to make this problem even hard, to make this question even harder to answer, we can step even further back and ask an even more basic question. Why do we need brains? Like, why do machines need machine learning? Why do humans need human brains? And there's a very kind of reductionist answer, but that I think is very enlightening, that was stated by Daniel Walpert very concisely. He said, we have a brain for one reason and one reason only, and that's to produce adaptable and complex movements. Movement is the only way we have of affecting the world around us, and to understand movement is to understand the whole brain. That might seem kind of reductionist, basically saying like the reason you have a brain is so you can move your limbs. But there's something very true about that, that like it only is the decisions you make that affect the world, not all the processes and predictions. And we could postulate a similar thing about machine learning, that we need machine learning for one reason and one reason only, and that's to produce adaptable and complex decisions. So it's the capacity of the machine to make decisions that really determines whether it got anything useful or not. And that's obviously true for robots and autonomous cars, but it's even true for things like computer vision systems, because if you're predicting an image label, you are really making a decision, and that decision affects something that happens. So it might not be the label itself, it might be what happens with that label afterwards. If you tag a user in a photo, well, that affects how that user will use your website. If you detect an endangered animal in a camera, that might affect some downstream conservation efforts. So all the outcomes of these systems are decisions, and if we treat them as decisions, that maybe brings us closer to the true goals, the reason we want to build those systems in the first place. And taking that bit of philosophy and using that to inform how we should think about pre-training on diverse data might lead us to a conclusion like, if we want our models to make decisions, pre-train them to be good at making decisions. So what's a decision? Well, if we write this out in potentially gratuitous math, we can say that like xt represents the present, and in RL this would be a state. Xt plus k represents some future outcome, and a decision is an action that you pick, something that might change that outcome. And informally, you could say, well, a decision is like P of AT given xt comma xt plus k. What is an action you could take that will lead to the outcome that you want? Okay, and this is a little bit hand-wavy in terms of the definition of these quantities, but of course, in RL is something that should be very familiar to us. And an idea that we could formulate for self-supervised learning that might get beyond this issue with modeling the density is to say, well, what if we learn how to take actions to produce any possible outcome? So if what we care about is producing is decisions, and decisions are about producing outcomes, let's pre-train to produce a wide variety of different outcomes, and that should be really good pre-training to then fine-tune and produce the outcome that we really want. And we can make all of this like information theoretic if we really want to, because then we can maybe better understand it. So the more principled version of this is to maximize the mutual information between your action, maybe a latent action like Z, and a future state xt plus k. And as an objective, this has some really interesting properties. So this is sometimes referred to as empowerment. There's lots of papers about doing this for unsupervised RL, and I'll actually talk about that a little bit. So don't want to get into that just yet, but there's a deeper information theoretic notion of what training for all possible decisions really means. Okay, so to kind of close out this motivation, maybe we shouldn't ask what self-supervised learning can do to help RL, but we should ask what can RL do to really help self-supervised learning. So if we can take actions to produce any possible outcome, that seems like it could be really great pre-training. And this is basically a goal-conditioned or task-conditioned or skill-conditioned reinforcement learning problem, where we have our small task-specific data set to get the outcome we want. We have a large garbage data set, and that large garbage data set now will not be used to match the distribution in the data. It'll be used rather to illustrate all of the possibilities available to us so that we can learn to achieve outcomes. So we'll do some kind of self-supervised, maybe goal-conditioned or skill-conditioned RL loop on that garbage data, treating it as a space of possibilities rather than a supervision on our behavior. So this would allow us to learn about how the world actually works rather than trying to like imitate everything that was done on the internet. So of course, there's a little bit of an issue here because this is a data-driven process. the whole point is to pull in data. On policy RL is probably not a great way to do that because that requires actively interacting with the world, and the world exposes itself to us not through active interaction in this case, but through a large data set that we might mine from the web. So with naive RL, this is an interactive process that's pretty difficult. So what we would like is a data-driven process, and that means doing offline RL. So putting those things together, let's learn to make all possible decisions using offline RL from plentiful data that we've already collected, and use this as universal pre-training that'll help us make other task-directed decisions for any downstream task. So then the kind of notional recipe is we start with a large data set of possibly low-quality stuff, this kind of garbage data set, basically all the things that our agent has tried to do in the past, or everything that we saw other agents doing on the web, videos of people interacting with the world, whatever source of data you have. Perform some kind of self-supervised offline RL on this, and there are a few choices: human-defined skills, goal-conditioned RL, self-supervised skill discovery, and I'll talk about a few choices for this. And then learn a downstream task. I'm going to discuss examples where this downstream task is always an RL task, always a control task. But even that doesn't have to be the case. Your downstream task could even be a prediction task, an image classification task, a video segmentation task, or something like that. And insofar as machine learning is about making decisions, pre-training for making decisions should in principle be useful for whatever other problem you have downstream, because that problem is a decision-making problem in disguise. All right, so that's the setup. And what I'd like to tell you about today is some recent work from my group that gets at things that might be perhaps good building blocks for this kind of recipe. I'll talk about algorithms for self-supervised offline RL pre-training and some recent progress we've made on using ideas about metric spaces to improve self-supervised pre-training. I'll then discuss how we can further extend these pre-training recipes to train on data without actions, because when we're training on all sorts of data from the web, maybe we can pull in videos and things like that that are not MDPs in the traditional sense, but can still be used as pre-training for these self-supervised procedures. And then I'll conclude with just a few slides showing how some of these ideas can be applied to real-world problems in robotics. Okay, but let's start with some more algorithmy things. So first, how do we pre-train with RL on unlabeled data, right? So we discussed how it should be offline. We discussed how it should propose tasks and achieve a variety of possible outcomes. So a very simple answer, and a very popular answer in the literature, is to go with goal condition policies. So a goal condition policy is a policy that takes an action given a state and a goal, and its reward function is simply an indicator for whether it achieved that goal, whether it, in the future, whether it entered a state that is equal to the goal or very close to the goal. Unfortunately, training goal condition policies like this can be extremely hard. It's actually a little bit of a mystery as to why it's so hard. There are a variety of possible answers, and I'll talk about one of them, but I just want to acknowledge up front that goal condition policies seem to be a lot harder to train than single task policies, and the truth is that we don't know exactly why, but we have a few ideas. One idea that we studied in this paper called HIQL is that it has to do with how vulnerable the policy is to small imprecision in the value function. So imagine that we have this grid world environment. The goal is the grid cell marked in red, and the color here denotes a value function that we trained. This is actually a real value function that was trained with a real RL algorithm. The value function is pretty good, but it's a bit noisy. And you look at this thing and you kind of say, like, yeah, it sort of makes sense. Like the values seem to be higher closer to the goal, they're lower further from the goal, and there's like a little bit of error in them, so the value function is not perfect, but it roughly gets the right idea. Like this seems like a pretty decent value function. Except that if you take that value function and you compute the corresponding greedy policy, the policy is terrible. And you can see that in many cases, this policy, which is the greedy policy for the value function on the left, actually moves away from the goal. So the arrows marked in red actually show states where you not only don't take the shortest path to the goal, you actually move away from it. You actually make it worse. And that's a really big problem. So the point is that when the goal is far away, even small errors in the value function can translate to significant errors in the policy. Basically, it means that the signal to noise ratio in the value function gets pretty bad. And that makes a lot of sense because the value function is going to fall off exponentially with discounting. So that means that small errors further away lead in the value lead to pretty significant errors in the policy. Bad signal to noise ratio. And it turns out that there is a very simple trick inspired by hierarchical RL that is actually a lot simpler than most hierarchical RL methods that allows us to deal with this. So the idea is actually very simple. It's an idea that has been studied before, but we have a particularly simple instantiation of it. The idea is that we'll have two policies, a low-level policy that looks at a goal and produces an action, and a high-level policy that looks at a distant goal and produces an intermediate state. So this intermediate state, st plus k, is going to be the action for a high-level policy. That's a very widely studied idea in hierarchical RL, but one observation we made is that this idea can be leveraged in a very simple way once we recognize that a big part of its benefit is dealing with the signal-to-noise ratio problem. So our hierarchical policy is going to be recovered from the same exact value function. So we are not actually going to have a high-level actor critic and a low-level actor critic. We're just going to have one value function, exactly the same one as in the top left, that noisy one, where if we take that value function, we recover a full goal condition policy, that policy is bad. It turns out that if we take the same exact value function and we recover a low-level short horizon policy and a high-level long horizon policy that predicts states, the concatenation of those two policies will be much, much better. And that's actually kind of surprising because most of the hard work is being done by the value function. So simply by changing how we do policy extraction, having this hierarchical extraction strategy, will get a better policy. And the reason that makes sense is that the high-level policy is less vulnerable to that signal-to-noise ratio because its actions are over more steps. So a mistake over one step doesn't affect it as much. The low-level policy only deals with near-term goals, so it's also less affected by the bad signal-to-noise ratio because it never has to deal with goals that are so far away that the exponential discounting creates this vulnerability to SNR. So to summarize the method, one value function, the value function is over the low-level single time step granularity, two policies, low-level, which outputs actions for nearby goals, high-level, which outputs states for distant goals. The value function is trained with offline RL. It uses a method called IQL, which is basically performing expectile regression. So roughly speaking, it approximates the max over the future successors at the next time step using this kind of asymmetric squared error loss. So if you want to learn more about this, check out implicit Q-learning. It's a fairly standard offline value learning method. And then once that value function is trained, we just recover two policies from it using a variant of advantage weighted regression. The high-level policy and the low-level policy are both recovered with weighted regression, and the regression weights for the high level are given by the difference between the value of the distant state and the current one. For the low level, the difference between the value of the next state and the current one. And I think there's something pretty profound about this because the policy extraction is a purely greedy process. The policy extraction is not trying to do long-term Bellman backups. Only the value function is doing that. The value function is doing it over a granularity of single time steps. So the value function training is not hierarchical. It is very simple, exactly the same as previously in the literature. The only thing that changes is that the policy extraction now has this hierarchy. And that hierarchy addresses the signal to noise ratio. And we find that this does a lot better. So these are IQM plots. These are the full tables with the numbers. The IQM plots are a lot easier to look at because they summarize, they average over multiple tasks. And a very relevant comparison here is HIQL, which is this hierarchical method. That's the red bar at the top, versus IQL, shown in green, which is basically the same method, but without the hierarchy. And you can see that there's a huge improvement in HIQL over IQL, even though they use essentially the same value learning method, and they differ only in the policy extraction. So just by having that higher level policy, we suddenly become much better at this kind of self-supervised goal condition training. And you can also visualize this process. So here you can see the ant maze. The little blue circle is indicating just the XY position of the goal state. The goal state is a full state, but here we're just drawing the XY position for your visualization. So that's the high level policy, and then the movement, the actions at the joints are the low level policy. And you can see it's doing something very interpretable. So it's kind of leading it by the nose towards the goal. So that's pretty cool. That means that we can just change the extraction strategy and do better at this kind of self-supervised learning. But of course, not all tasks are goals. So we could say, well, what about more general skills? What about skills that are not just about matching a particular desired states? In the past, when people have asked this question, oftentimes the go-to class of techniques have been information theoretic methods, methods that are about that mutual information equation that I had in the beginning, maximize the mutual information between some representation of a skill, some command, which is often denoted with Z, and a future state, xt plus k. And the reason that this is a pretty natural objective to use is that the mutual information decomposes into a difference of two entropies. Maximizing mutual information means maximize the entropy of future states you could visit, which is to say visit as many states as possible, but minimize the entropy conditioned on your skill, which is to say once you command a skill, for that commanded skill, the outcome should be very predictable. So you should have many possible outcomes, but they should be very predictable given a particular skill. And that basically trains your model to be able to reach a variety of states on command, achieve desired outcomes. That's more or less exactly what we're motivated with. The trouble is that if we directly use this information theoretic objective as a reward in self-supervised reinforcement learning, we end up with an extremely difficult and kind of underspecified RL problem. So this is a widely studied formulation. It's been studied now for quite a long time. In fact, there are even older papers than this going back to the original work on empowerment that go back decades. But it has proven to be quite difficult to get methods that are truly scalable for the pure version of this objective. And there are a number of reasons for this, but if you want to get a little bit of intuition for it, the mutual information objective is saying that you should have the outcomes be mutually predictable from the skills. And if the number of skills is limited, the mapping between skills and outcomes is not very well defined. So, for example, if you have this kind of X-shaped environment, even if your agent travels just a little bit in the direction of each of the legs of the X, just a small distance, it doesn't cover the whole space. It might still have a very predictable mapping because there's a lot of information contained in those states. And if you think about, the real number line, it's not countable. So if you visit all the numbers between 0 and 0.5, from a mutual information perspective, it's just as good as if you visit all the numbers between 0 and 500. So the trouble is that in its most basic form, if you have infinitely many skills, you will eventually cover all the states. But for a finite number of skills, or even an infinite but lower measure number of skills, it's actually very tricky to get complete coverage. So maybe what we can do is we can take this starting point and augment it with some kind of notion of metric that tells the agent that all else being equal, it should cover the space. It should go everywhere. So can we develop a general offline unsupervised skill learning framework that is based on metric spaces and learn skills that maximally span the space? And of course are also predictable and have all the benefits of that mutual information objective. So based on this idea, we developed something that we call Hilbert Foundation policies. And this is work that was primarily led by Sehon Park. And the idea is to first start with a representation learning step where we're going to learn basically metric representations of our MDP. And there are a variety of ways to formulate these metric representations. You can even make them quasi-metrics if you want to be more general. But if we're willing to cut some corners, we can say, well, let's just have it be a metric so that distances, let's say even Euclidean distances, in that space correspond to temporal distances. So how many time steps it takes to go from one state to another is close to the Euclidean distance between the embeddings of those states. For general MDPs, by the way, this cannot be a metric because it can't be symmetric. So for more general classes of MDPs, this might need to be a quasi-metric. And there are some ways to get at that too. But for now, let's keep it simple and let's just make it a metric. If we can train such a representation, then it turns out that a really great way to develop a self-supervised RL method is to simply take directions in that feature space as rewards. So if we have a representation of our skill Z, we'll represent those skills as vectors in the same space as our representation and take the rewards to be dot products between the difference of the future state and the current state and this vector Z. So essentially linear rewards in this representation space. And while it's not immediately obvious, we can show that all linear rewards in this representation space promote your policy to cover the space, meaning that they will actually get you skills that go as far as possible along the different directions in your state space. That's the self-supervised procedure, and that self-supervised procedure is trained with offline RL and offline data. But once you train it, it turns out that there are some very nice ways to recover policies for specific outcomes that you want to achieve. So once you train this policy condition on Z and this representation phi, you can, for example, extract a skill for a particular reward function simply by doing L2 regression onto that reward using Z's as the weights. So basically, if you have some reward R that you want to solve for, just do least squares regression in that feature space that you learned, and then take the skill corresponding to Z. If you want to do goal reaching, again, you can take your goal, subtract the current state, the embedding of the current state, and treat that vector as the Z. And again, plug into the same policy that you got from pre-training. And of course, if that doesn't solve it in zero shot, you can use it as a starting point for fine-tuning. we evaluated this procedure on XORL, which is a zero-shot reinforcement learning benchmark proposed in the literature. And we found that this procedure does significantly better than a variety of previously proposed methods for these kinds of zero-shot problems. One of the techniques we compared to here is the FB representation, which was basically the methodology that was used in the paper that proposed the benchmark. So this is getting us a pretty good performance on a previously established benchmark for these zero-shot RL problems from offline data. Okay, so this was about self-supervised RL methods, but still methods that operate under what we would call kind of standard assumptions, in the sense that these assumptions still assume that you have data from an MDP with states and with actions. In the next section, I want to talk a little bit about what we could do if we have data without actions, which is maybe more representative of data that we might get from the internet. So what if we have prior passive data, which might come from other kinds of dynamical systems? Maybe they have a different embodiment, different action space than what we want to control, or even data without actions like videos. We're going to try to train something on this data, which I'm going to call an intention condition value function. It's also going to be conditioned on skills, Z, but now it'll be conditional on skills and outcome states S+. So it'll kind of combine both of the ideas from the previous section. And it will not have actions because there aren't actions in the data set. So these intentions, these Z's, will take the place of actions. And once we've trained it, then we can use it as an initialization for downstream RL. So I know I'm running a little short on time. So what I'll do for this one is I'll actually provide some intuition for what intention condition value functions are. I'll skip over most of the math, and then I'll just discuss a little bit of the practical implications. So to build the intuition for this, let's say that we have some data with actions, maybe from our robot, and then we have a lot more data without actions, let's say from videos. What can we learn from the videos? Well, here's one way to think about it. Let's say that we have a video trajectory that goes through two states, the green state and the orange state. This immediately tells us something. It tells us, for example, that orange comes after green, meaning that if you are in green, you can reach orange. But let's say you have another video that goes through blue and yellow, and blue is very similar to green. Now, since blue is similar to green, you might be able to infer that green can lead to either orange or yellow, because yellow follows blue and blue is similar to green. So this is an inference that you can make from videos, even though you have no idea which actions led to those outcomes. So more precisely, you can say that if you're at green, and if you try to reach yellow, you will likely reach yellow because yellow was reached from other similar states. So the key idea is to use videos to learn which outcomes can result from which states. And this turns out to be a great way to initialize value functions for these kind of general purpose self-supervised objectives. So more precisely, the intention condition value function is conditioned on the current state, S+, which is that yellow state, the thing that you will reach, and Z is a latent variable that basically explains why you went to yellow or orange. Z essentially determines the actions you will take, except that since you didn't have actions in the data set, you don't necessarily know what those actions were. You just know that there exist actions that can make that possible. So it's a kind of latent variable model where the latent variable represents strategies. Strategies are patterns of actions. In the interest of time, I won't go into great detail about how this is trained, but the short version is that the training procedure is very closely related to successor representations, going back to the classic Peter Diane 1993 paper, and very heavily inspired by something called FB representation. So we have a multilinear representation of V in terms of features of states, features of outcomes, and a matrix determined by Z. So the full math is in the paper. I'll skip over this because I'd like to make sure I end on time. But what I will cover briefly here is the outcome, the results. So for the results, we're going to fine-tune from this intention condition value function to predict Q values for Atari games, and as well as other benchmark tasks. And for the Atari games, the pre-training actually comes from videos that are scraped from YouTube. Basically, people post videos of Atari games on YouTube. Those can be used for pre-training. And the bar graph at the bottom shows fine-tuning to individual Atari games from a variety of representations, with ICVF being the one denoted in purple. Okay, so just to wrap up, the last thing I want to mention is that we can actually take these ICVF ideas and we can actually use them with real robots. So we can actually have a multi-phase training procedure where we first train ICVFs on real videos from the Ego4D dataset, then fine-tune on robot data, and then actually fine-tune from there to individual robotic skills. And this actually leads to robotic behaviors that are more effective than those trained only on the robot data. Okay, so I think I'll stop there. I think that I went a little bit long, but I'll be happy to take any questions if there's a bit of time.